Right, hello everyone, welcome to another stream. How's it going? Let's post that we're live. Cool. Right, so today we're going to carry on with writing the voxel map data structure. We're currently trying to write this function. It looks a bit complicated. It's a bit crazy, but we wrote most of this out last stream. And the basic idea is we've got a voxel map mutator, and the idea has a voxel map which defines its dimensions, right, x, y, z dimensions, and a root node index. It is a tree which has 64 children, so 4 by 4 by 4, and for each node, and that recurses down until you reach the map size, basically. And the idea is that we want to try and render a very big map. So it's going to be 1024 by 1024 by 256 meters. So it's quite a big number already. But furthermore, we'll make it even bigger because each meter is going to be a 16 by 16 by 16 block of voxels. And so that means it ends up being this stupidly big number of this many voxels, which is, very hard to render. So we're trying to make a data structure which will both store, will basically pack everything down as much as it can, but will also only store data that it needs to store. So stuff like air voxels won't store anything, and things like voxels which are buried, because we're not going to have any like ways to dig in this game. Those will not be stored in this tree also, and we also want to make it such that we can use this data structure to traverse through the map very fast as well. Now, so effectively it's like a sparse voxel octree, but it's not an octree. It's instead of 2 by 2 by 2, it's 4 by 4 by 4, right? Now I saw a good one on here in the past, but I can't see it. We'll do a visualization like this when we do the ray tracing. So it's like a heat map basically on how many nodes it traverses through. But yeah, we've got some good diagrams. I've managed to make some good diagrams off stream. Oh, here's the one I wanted to show you guys in it. Let's get the chat up. Here we go. Right click there and keep that one above there. Right, yes, this is one I was looking at last stream. Oh, for crying out loud, the web is ruined. Right, let's pop that up there. Yes, this is like an octree, but so areas that don't have voxels, right, the tree nodes won't go down that far, therefore it won't store the voxels, right? So this is how we get away with not trying to have this many voxels in memory, right? So we're currently trying to traverse down trying to write the function which basically says, hey, I want to set a voxel to this particular material index, right? And we're currently just trying to set a specific coordinates, like traverse down that tree basically, and this recursively goes down the tree and keeps trying to make nodes if they don't exist, right? And that sort of thing. So I made these lovely diagrams off stream. Basically, these are like the first things I've like vibe coded because I don't typically do that, but I was asking AI about seeing if it can make me an image. And turns out it could make me HTML files. So I've managed to make it give me these lovely things, these interactive diagrams to help you guys and also me think about what the code is doing, right? So it's pretty cool. So what we're effectively, this is the next problem we've got to solve. We've got to make it such that our block metadata all kind of fits into cache lines, such that when we access these things, such that when we access a neighbor block, it will pull in all the metadata for the ones next door. So when other threads try and access those, they'll already be in cache, and we won't be wasting memory in cache, basically. Because if you imagine this was a bunch of, imagine we pulled in this guy and it was next to memory that was never ever read. That'd be a waste of data in the cache line, right? So we want to leverage this as much as possible, because when we traverse through the traverse through the structure, we want to pull in as much data as we can to reuse. So if we start off with a prayer, then we'll get into exactly this problem that we're trying to write code for next, and I'll go into a little bit more detail. But yeah. Father in heaven, we thank you, Lord, for this day. We bless your holy name. We thank you, Lord, for the grace and your mercy to be alive. We thank you, Lord, for all the things that we have in our lives, like the food on our table, the cars on our drives, and the our family, our spouses, our children, and our wonderful homes that we have, Lord God. Father, we pray that you attend to every need of ours, every need of my viewers, Lord God. Attend to their needs. If they're going through a hard time in their life, Lord, please send the right people, send the right help into their lives, where you will pull them through that situation in their lives. Thank you, Lord God, and let your name be glorified in that situation. Thank you, Lord. Lord, we just pray for your, your continued mercy. Please don't let the enemy use things against us. Don't let him, Lord, destroy our lives, and help us, Lord, put us in positions for you to use us to do great things for the kingdom of God. And we just pray that you use us to touch many people's lives and bring them to salvation, bring them to the way, the truth, the life, which is Jesus Christ, and bring them to the mercy and the love of God. And we pray for your divine touch to give us your divine wisdom and understanding, your divine counsel, Lord. We pray that we'll be dependent on you and you alone. We're not dependent on any anything the enemy wants to provide. And we just pray that you be with us and dwell in us, and help us not let you down, and quench the Holy Spirit. Thank you, Lord God. In Jesus' name we pray. Amen. Cool. Right. I hope everyone's having a good weekend so far. God bless you all. So yeah, we basically wrote some code where we're trying to say, right, I want to write to this sort of coordinate a voxel. Please make sure all of the nodes in this tree, I've got two web browsers now, so imagine there's this sort of tree. I guess this is a binary tree, sorry, an oct tree, but we've got 64 tree, but it's similar, right? So this is the first node, that first cross, where you got these 4 quadrants here, right? And you basically keep going down and allocating those. Say if you want to put one in this here, you'll basically keep descending down this guy. Oh, it doesn't need to be made. Oh, it doesn't need to be made. Oh, one needs to be made inside here now, and it'll split that into 4, basically, right? And then keep going down and down and down. So it's a little bit more complicated, because we're trying to make sure stuff stays in cache lines and things are next to each other. So if, in our case, if the node gets a new child, what's the way of saying it, which is active, it's gonna like potentially have to reallocate all of the siblings into another place, so all the siblings fit into a cache line. And this is what we're gonna have to do here. So we're currently trying to, well, it's a bit different. We're trying to now, so if it's not so if it's a leaf node, so a leaf node is going to mean it's the final 4x4x4, right? We're seeing it in 2D obviously because it's just way easier to see, but the final leaf node is this 4x4x4, right? And then what we can do is then access the block that it is in, and the block is going to tell us where the array of voxels are and how many bits per voxel, which is a thing we'll see in the future. I've got another diagram for that, basically. And what we're trying to do right now is make it such that when you get down to the root node, it stores. There's two things that it stores. Where is it? It's the voxel shared ENC, this boy. So there's a node cold. So there's a node hot, and this just stores 64 bits for the children. There's a 4x4x4 fits into that, right? Because 4x4x4 is 64. And when you ray trace through that and hit a voxel, right, then you can go over into the parallel array, into the cold data. So the cold data only gets accessed when a hit happens, right? Because if you don't get any hits, there's no point pulling that into the cache, right? That's in a separate thing. It tells you if it's a leaf node or not. And if it's a leaf node, it's the final 4x4x4. So that will store a block index instead of a children start index for the next node. Now, this block index is what we're trying to allocate properly, right? How do we get the blocks next to each other such that all the neighboring blocks within some kind of region are in the same cache line? So what we're planning on doing, so it's a bit different from the end of last stream. At the end of last stream, I was like, oh, it won't be a problem. We'll just do a free list and allocate them all over the place. But I was thinking after the stream, it would be easier to do that. But if we think about it now, we can just solve the problem. And this is what I've come up with. So the basic idea is we're going to call something a chunk. That's 64 cubed, right? 64 by 64 by 64 voxels. And this is the red thing. So effectively, all of the blocks which are inside of a chunk will have their block metadata in the same cache lines, maybe, right? So as you see, per 4 blocks will fit into a cache line. So if we see the block data, it's just a material start indices and a material palette index. And maybe we might store like how many bits per voxel there is as well. We'll figure that one out, but it wouldn't be too hard to bit pack that in. We can we can reallocate some bits from these, right? Because stealing, that's a sin. We can't have no sin in this code base. But yeah, you get the idea, right? So basically, you see, this is just 8 bytes per element, right? You get so every time we reallocate a new block of 16 by 16 by 16 voxels, so you're just traversing through the tree, and that's just another 4x4x4 node, and it's just got to this level, which ends up being 16 voxels wide, and that'll be called a block. And this splits down into one more level there of 4x4x4, and then another level there. So there's 2 more levels down until you get to the, well, 1 level down until you get to the final level of 4x4x4. Yeah. So when you allocate a new block, which we can keep track of in the code, we need to say, right, go back out to the parent, and that's a chunk, scan through all of the children and find the minimum block index and the maximum block index. That'll get you a range of where they are in memory already. And then see if I were to add another block, does it span more than a cache line? If it does, right, we need to then reallocate all of this metadata such that the two cache lines sit next to each other in memory. If it doesn't, we just need to do a mem move and insert the new block metadata basically, and then reassign all the indices back down the tree to the children. And that will mean when you're traversing it, all these block metadata will sit next to each other in memory. And as you can tell, they're tightly packed, right? So if 0, 3's allocated, it goes first, right? And then 4. And we might want to do some more on swizzling here, so they're in a lovely Z curve, right, order, which this doesn't really show. But you get the idea, right? So because we allocated an extra 1 here, it would have had to reallocate the 2 lines together. So this is the code we're going to be writing, and then we can move on to the next one. But yeah, if you want to play around with these guys and see what they're like, they're on the Discord channel. They're in the programming section, I think. Yeah, discussion programming. I've just dumped them in here. Because it's my first experience using AI just to say, make me this. And it was pretty cool. It took me 45 minutes to make these 2 diagrams. So this is one we'll be looking at next, basically. And it's quite right. Just quick documentation, basically, and ways to interactively understand things. So this is the complicated code. So the basic idea is we've traversed down from the root node, which is 4x4x4, and every time we're sort of dividing by 4, finding which one of the 4x4x4s we land in, and then work out like the actual index of the child, and then you get the child node index. We see whether or not the child is missing, or if it needs to be copy on write it, do a copy on write this frame, and we get the number of children, and if it's not a leaf, do we need to say if it's a block or not? Is that what I'm trying to say here? If it's not a leaf, oh, and this is saying if it's a leaf. Yes, if it's a leaf, find the block index. Yes, this means we need to create the node now, isn't it? Yes, if it's a find the block index. So we go back up to the block node, which we would have passed in the past. So we would have found like, hey, if the dimensions of it were 16 by 16 by 16, then that will be, hang on a minute. Yeah, this should only happen if it's a, oh yeah, sorry, this is when it's a leaf, sorry. Yeah, so that means block node index shall be set. So we should be able to traverse down from the block node and find one of the children, which will basically tell us like what block it is in. So basically imagine one of these, this is a block. We're talking about one of these final 4x4x4s, and that's a leaf node. So we would remember where this block was, which is splits down into 4x4x4. Oh, sorry. The final 4x4x4 will be here. Is this diagram a little bit off? Or is my understanding a little bit off? What's going on? Because that'd be a binary tree. That'd be an octree. Oh, no. Yeah, sorry. Yeah, okay. So the final, I'll split this into 4x4x4. So that would be this. No. yeah, so it's each of these guys basically 1, 2, 3, 4. Right. So yeah, 4 there. And then inside here there's another 4. So yeah, so this code here that we're talking about. So it'd be one of these final leaf nodes here, basically, one of these like 4 by 4 by 4s. And so we remember this block, and we will be traversing through this tree and just chasing the first child and just seeing like, hey, what block is this first child in? Because the last node stores when it's a leaf, it stores the block index. So we're just looking at a neighboring node, and it tells us what block it's from, and that's what block we are from now. So when it's creating a new leaf, we're able to look at the neighbors and know which block it's from. So if the block is not equal to U32 max, so that means that it exists. Yeah, we might need to handle one else here. Is that true? This is starting to do like reallocation. It would just need to allocate regardless. We need to put an else up there and think about that in the future. Okay, so now it's going to be like, right, the chunk, which is the 64 by 64, so it's this red one here, which stores all the blocks, where the metadata all sits together in a single cache, well, in cache lines which sit next to each other in memory. We say, right, now traverse through all your children from the 64 by 64, so these 4 by 4s by 4s, and find the minimum and maximum block range, and that will tell us the allocation range which it currently is at. So there's lots of traversal rather than storing stuff in the nodes, because we're trying to preserve memory here, and we don't mind mutating the tree costing time, because it's all about maximum storage, but also traversal times, right? So we want to keep data packed as much as possible. So yeah, find the minimum and maximum range. Then we ask the node pool, do we need to allocate any more blocks? And this logic, basically, as we said before, is trying to say, so blocks count. So that'll just be a end take start. See, as we said before, if we span over a cache line, well, you need to now allocate another cache line. So you need to basically reallocate into a different area, basically. And that's what this code is doing here, is allocating another one and then copying it. And then we do a mem move to insert the new element. So we do a difference to get the count. So with the blocks count right there. And the new count, we're trying to say is something like, is child node missing? What do we mean by that exactly? So the node, it's a leaf. Oh yeah, so we will come and see if the child node is missing or if it needs to be a copy on write. Yep. So sometimes we're just trying to do a copy on write. And hang on. Yeah, so if we're trying to do a copy on write, then it needs to be this logic up here. Where if it yeah, if it's not missing, do this. What's that doing? So if the child is missing... No. I think it's the wrong way around. So if the child is missing, you want to basically just do a clone. Then if the child is not missing, no, 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 no. I'm a bit confused now. So, right, I think I need this as a Boolean. We'll call that needs copy. Right, so when we mutate it for the first time this frame, we need to do a copy because the renderer could be using is going to be looking at that node in the past, and we want to keep it around for a few frames. So in that case, we want, yeah, I think I got this a little bit confused maybe. So if we, like, could the child be missing and you need a copy? But yes, I think it needs to be, I think, yeah, that is true. So I think either it's need a copy or we need to reallocate because the child is missing, that sort of thing. Yeah, both could be true. That would be fine. Okay. But so if the child is, I think I was using that as a way of saying it needs to be copied, right? If it's not missing, but we've managed to get into here, then it needs a copy. Yeah, I think that was it, but I think it just makes a bit more sense if we just do needs copy. So that means, yes, only if the child is missing. We want to do the shifting over. Yeah, that makes a lot of sense. That's good. Okay. Glad I remembered that. That's good. Cool. So here we just want that to be a needs copy, so that is going to function properly. So we allocate, do we need to allocate new blocks or do we need to copy? Great. So go ahead and allocate those new blocks. Make the new node point to the new region, copy from the old region to the new region, and deallocate the old set of blocks, right? Cool. Then if the child is missing, perform the copy. Right, how do we handle this? So perform the mem move basically, right? Shift and insert. Yeah, I wonder if we've got the insert here. Anyway, we'll figure that one out. So regardless, we need to, yeah, I guess you just do this again. So you can just call it start. And then just do something like this, I think. And then that'll be shifting. And then we zero the current block data. Amazing. So if it doesn't exist yet, what is this doing here? I think is a bit questionable. Because this works it out based on the bit set, doesn't it? And the bit is not even in there yet. like, ooh, well, if the bit is not there yet, then it will be looking at the, yeah, it does a -1, so it's looking at the stuff before it, so it should be fine regardless. And that's where the new one will go. That's pretty good. Cool. Right, so this will then allocate the new, so it gets the existing block range by going from the chunk, going down until the absolute root, so this is 64 by 64 by 64 voxels, and we keep subdividing into 4 by 4 by 4s. So one layer is this block layer, then the next one would be this and these 4 by 4 by 4s, right? 1, 2, 3, 4. And then inside there, the next layer will be 1, 2, 3, 4, right? So it descends down all those layers and looks at that final leaf node, and that tells you the block index, and it gets the min max. So we get the count, and we basically, if we need to do a copy on write, or if we've added enough to go into a new cache line, we need to do some more allocations. If a child was missing, you want to basically shift the element over. So if we was to allocate 6 here, that's going to shuffle along 7. Interesting though, there is other cache lines. Yeah, it shuffles it across the whole thing, the whole allocation range. So that will work just fine. Now, the issue is what you've done is you've gone unchanged, right, where the block indices were, right, for all of the you've gone and changed where the block indices were for all of the siblings, right? Sibling blocks. So that means you've got to go down from the chunk and then sort out all of those block indices at the leaf nodes. Again, a bit expensive, but it's the trade-off we're making. So we want to basically say we want a function like this or something where it just keeps descending down. So how would you do it? So you'll go from the node and you'll be like, right, yeah, you'll go over all the chunks, figure out their sort of block index. Sorry, in the chunk, you look at all the children and figure out the block indices of the 4 by 4 by 4 and be like, right, you get this one, you get this one, and they all traverse down and store them. So you might want a separate function. Maybe not though. So that's a find. So it's similar to this one, I reckon. So find. So we could say store or update or set new block range from chunk node. Index, there you go. Of chunk node, something like that, okay? So we're not going to return anything, obviously, because it's a store function. And we need to have some kind of like block range. So, right. Let's go back to that place. We'll just dump it here. We've still got to do the else statement, but that's all right. So it'll be chunk node and block range. Now the thing about block range has now been changed. So the variable hasn't been updated. So in this case, it'll be, well, it only happens when the reallocation happens, right? And that is this code here. So this means we can say block range dot start equal new start. And then we do a lovely, hang on a minute. Oh, this is the range here, isn't it? So we'll call this the Well, no. We're only interested in doing like a block range dot end plus children count. Sorry, where is it? New start plus children count plus if a node is missing. There we go. So now when we get into it, we've got a new lovely block range. So we get the hot, which stores the bit set for the children nodes, and the cold as well, which stores the the index to the start of the children where they live in memory. And it should not be a leaf, right? Basically. So we assert that. And we say, right, get the child nodes, get where they start, and we don't do this anymore. And I think we want to just keep traversing. So we might be able to call this the chunk hot, and we'll call this one the block hot. And then we'll call this one the chunk cold and the block cold. So the index we'll be using is packed children start index plus the index there. And so they'll be next to each other in memory, again, making it very cache efficient. They're all aligned to cache lines. So, it's not necessarily the best thing for, well, okay, it works all right for this, but the main reason why we do it is for the traversal on GPU, right? The reason why we have to do this algorithm in the first place is because they're in this structure. So a block has another 4x4, and then those inner 4x4s have the leaf node. So you have to go down to the next layer, and then the next layer. And I don't know. Yeah, should we do that on... should we done that in a function maybe? Because this one went down. Then it just looked... Well, it just looked there and then it... Hang on a minute. That was in the chunk. Goes over the children. Then it goes over the next layer of children, and those ones are the leaves. Is that right? Yeah, that's true. Yes, it's not that bad. So all I need to do... So it goes the chunk children. Is that right, though? Yeah, because from a block, you got children of... Maybe that's wrong. Let's think about it. So the block... Oh yeah, those children are the leaves. Yeah, that's right. That is right. Man, trees are like the worst data structure. If you could avoid trees, it's amazing. Like, you can pretty much avoid trees all the time. Except when you do stuff. Like, 99% of the time you can avoid trees. And it's amazing. Right, here we go. So I'll call this block hot. So, children count, I guess I can call this the block children. Sorry, chunk children. And this will be the block children. Then we want and there's another one here, one calls the chunk. It's not really a chunk index, is it? But yeah, it's like a chunk child index. And this will be the block child index. All right, we're getting there. So if we see it gets the cold, and yeah, what are we trying to do? Yeah, it says it's a leaf. That's perfectly fine. We're trying to store, right? So now all we've got to do is do the opposite of that, which is a set. And we're trying to set some kind of block index. And this is it, okay? So the block index has to be... Wait, they're linear in memory, aren't they? Yeah, I wonder if we need to do some Morton Z-curve stuff here as well, because we should be thinking about this right now. Because, you know, if not, they're just going to be like left to right, you know, like row major basically in memory, which they are in this diagram that we've you know, put together quickly. But a Morton Z curve kind of order is probably okay. But then again, thinking about it, like, how do you Morton Z curve that? Right? You don't, right? So, like, how many do you fit in a cache line, right? You fit... Yeah, I think usually you might have like something like this in realistically, something like that. So you might have like a few voxels here basically to cover that, you know, a few voxels in that block. And they go, you know, maybe then if you, well, let's move it around here then. So you can imagine like a landscape, right? It might look like that, where you have some voxels that go like this. Now, this is not obviously 3D, it's in 2D. So you're going to have like 4 more of these, right? So you will have probably like 4 cache lines in that case filled with those maybe. And they will happen in some kind of like... But how do you Morton code that? You get their coordinate and then you can Morton code that and then you sort it. It's not the best. Yeah, it doesn't really work out too well, does it? How do we do it in the... Well, we already kind of do... Hang on a minute, is the voxel shared? Yeah, we take the yeah, we already take the coordinate, turn it into a Morton code index, right? And then that's the thing we use to access the children exists when we go down the nodes, right? So we're already doing that anyway. So how does that relate to this? So when I go over... That's a good question. Maybe some of this is... Yeah, how are you working out what index you go into? Oh yeah, because it does the Morton code here to work out the offset, doesn't it? Hang on. Yeah, it does the Morton code, and then it does that to work out its index inside that. Interesting. So it's already in the Morton code order. Pretty sure that's what we're reading. So if that's true, and we're just going down and storing it Yeah, it's already in the Morton code order. So we don't have to worry about it here. Amazing. So, right, what do we do now? So I'm pretty sure then it is literally just chunk children. Yeah, you gotta get this right. It's the chunk child index, which is a block index, right? Dun dun dun. And that would be block range. Maybe you don't need to do block range dot start. You just need to do a block. Right. Blocks. Chunk blocks, or just a block start index will do. We'll change the function plus that and voila. Amazing. Right, so that's not too bad of a function. Right. That's super cool. I like that. So we don't need to update the block range anymore. We just need the new start to be passed into here, and it will set all of the neighbors basically to be the right values now. That's super, super cool. Big fan. And that should set. The issue is that might set itself as well. Am I right by saying that? Wait. It's going to set itself. Oh, yeah. That's fine. This is a different set of data. Yeah, that's really, really good. See, I'm wondering where we set the block data up then. There's other things to be doing about this block. I think that's the next task. But let's finish up this, and then we'll get into like talking about the block itself. So I'll just quickly finish that sentence basically. Yes, the block itself is like, you know, the voxels inside there, right? And pointing to the material indices, and they're a variable sized based on how big the color palette is, right? Is the color palette just got 8 colors? Well, 3 bits per voxel is all you need, right? That sort of stuff. To really save memory there. So what we're looking at doing now is sort of this if statement. It logically feels wrong. So let's analyze that bit. So we've found a block inside. Yeah, sorry. This means that we've come down the tree and realized, hang on a minute, we need to make a new node. And so we go, and this is a leaf node. And so we're checking to see within this block, is there already a block that's been allocated? So by that, so we're trying to allocate one of these final 4x4x4s, right? And we're just going out to the block, which is this 16 by 16 by 16, and we're trying to check if any of these guys have been set. And the leaf node stores the block index. So it's literally just checking the first child. No. It's checking all of the children. No? Why is it in a for loop? What silly code is that? That probably came from a copy paste. But yeah, let's sort that one out. Basically, you just say, right, if children count, and then you just do that. Right, just grab the first one. Jobs are good. Okay. Anywho. So this is saying like, right, we have one. And this, but we basically need to be doing this code, right? Now, the interesting thing is, how did the nodes work in the past? Well, they didn't have a thing to reach back, some shared thing to reach back and basically store, right? I think that's what we're trying to say. Yeah. So this is some shared thing. Yeah, so this one is just trying to allocate child nodes. So from the current node, I'm trying to allocate the children nodes underneath. Whereas this one is like, I'm at the base leaf, I'm at the leaf node, right? And I'm trying to see like, right outside of me, is there any other, is there any siblings in my sort of 64 by 64 region? Is there any sibling nodes at all? That's what that's trying to say. So this if statement is a bit weird. And we're probably looking at, what is block index? Was not used anywhere else at the moment. So why did I write that code then? What are we trying to achieve? So we now got this new piece of code. Has this been superseded? Right, this has been superseded then by this. Right. We're saying get the minimum maximum of all of them. Now it could be that there's none. Right, okay, so it's still a problem. So if they're both U32, well, yeah, there could be no children, so there's that. That's, oh, so then, right, that would then end up being U32 max, that will end up being 1. Right, it's not what we want, is it? So I guess we're saying if children count, do this, else return, get rid of the else, return core range U3200, okay? And so that will do that and give you 0 blocks. Then 0 blocks plus the fact one is missing or not. You would never need a copy. Wait, any copy missing? You'll never need a copy on a 0, 1. Well, that doesn't need inserting. Right, so that all this children's count is dangerous. That should be blocks count. That's copy paste issues right there. Yeah, that makes sense. That's really cool. Amazing. So that should be the code basically. So I can just give a quick recap for people who just joined in. And then we'll move on to the next problem, which is trying to actually allocate the voxels and the material data for those, basically where that lives. So effectively, we've got this issue where we've got metadata of where the blocks need to live, right? And so the system that I have is we want to, each voxel needs to store a certain number of bits to sort of say, to describe the material that it's using. So we've got each block holds a material palette index and it tells you where the voxel data is. But to make sure we're saving the maximum storage, we want to, inside these blocks, rather than saying when we get down to this level of 16 by 16 by 16, and just having like a big old bit set, which ends up being 4,096 voxels, which ends up being quite a lot there, even though there might be some small amount. we want to avoid that problem and kind of still do 4x4x4 nodes within these blocks. And then inside those 4x4x4s, there'll be another 4x4x4, and that's the leaf node right there. So the idea is when we get down to the leaf node, we want to know, hey, what is the block I'm in? So we can look at that material palette index and where the voxels actually are and read from that. So that's the next thing we'll be doing. But the issue we're trying to sort out is when we need to allocate a new leaf node and the block and the block doesn't exist yet, or there needs to be a new, yeah, the block doesn't exist yet. So say if you're trying to do 5, we need to basically fit all of this block metadata next to each other. So when we're ray tracing through these chunks in the future, all of this block metadata sits all in the same cache line, right? Because the caches on GPU is only so big, and we've got a big map as well. So we want to basically preserve memory. We want to make sure the data fits into cache lines. So when we hit or we use some piece of data, it drags in the neighbor data because that's the most likely thing to be reused. And it's not being filled up with a bunch of empty data or stuff on the other side of the map, right? And so effectively, this code that we're just written is when we hit a leaf node, we go up to the chunk, find the minimum maximum range of where these exist inside the range of memory which holds all the blocks. And we say, right, when we add another block, let's say we're adding this one here, or let's say we're adding 5, right? When we add a new block, do we need to allocate any more cache lines? And if the answer is yes, we then need to reallocate all of these to a new section, copy it over, and then do the mem move, right, which inserts it into the right place, which moves them all over, then inserts that into the right place. Yeah, and that's what this code was doing. So I had another thought. What was that thought? Oh, I should have put a pin in it. This is why it's good describing stuff again, because you get to rethink about the problem and find bugs, but I lost it now. What was it to do with? So I was mentioning about these final 4x4s and yeah, something about a block not being a node not being allocated yet, and oh, I'm so close to that thought. I can feel it. There was something about so when you allocate this final 4x4 or the first 4x4. No, I lost it now. Right, let's just double check the code and then maybe it'll come back in that way. So we're on the leaf node and we've found out, or we're about to access the leaf node, but we're about to find out that the leaf node is missing, or we just need a copy because it's the first time we're mutating at this frame. I think that it might be something to do with that. So we've got a range. We look at the chunk, which is 2 layers up, and that's 64 by 64 by 64 rather than this final 4 by 4 of voxels. And we find a range. That range can end up being 0 to 0, or it can end up being something that gives us the block count. We say, right, if it needs a copy, or we end up going past the cache line and it needs to be reallocated, we allocate the new blocks, get the old one, set up, like point to the new location, mem copy over the existing ones into the same place they were at, just in the new allocation, and then deallocate the old blocks, the old block data. That's the new start, and then traverse down from the chunk again and make sure all of those other blocks, child nodes of the blocks will point to the new allocation, basically. Hey there, Wolfie. Yeah, this is all C. Yeah, just yeah, C11 or something like that. But yeah, you know, when you see, I'm not sure why the bot didn't do that, but yeah, you know, just find it a lot easier to work with, basically, and a lot less tempting, you know, to use features that will ultimately not give me wins. So pretty cool. Do quite enjoy it. You know, it has a few rough edges here and there, but you can quite easily avoid that. You got some engine tool you're working with, or pure C? No, it's just all from scratch, custom engine. Can't show anything at the moment, but there's videos up on YouTube where you can see some bits in the past that I've been working on. Like I've got a Magica Voxel importer, basically. Yeah, it's all written from scratch in C. All these modules here, custom GPU layer on top of Vulkan, custom graphics layer, yeah, custom UI, OS layer. Yeah, good fun. Lots of fun. So then if the child was missing, you move it over. Yeah, I can't think of any issue or that thing that I was thinking about before. It cannot possibly think what it was now. Oh well. It's the way it is. Cool, but it means we can move on, which is amazing. I think even amongst the non-religious people, you find the argument that C++ allows satanic code in style. Yeah. That's the thing, isn't it? It's that temptation, right? It's that Satan trying to tempt you with, like, to do a sin, right? And that's it is what, like, C++ is like, right? You're being tempted into using inheritance because, like, oh, I get to reuse these fields, right? Or you've been tempted to use templates because, like, oh, it means I can, you know, I don't have to copy and paste these functions 16 times, right? You know, 16 being the number of primitive types, basically, right? Which, sure, sometimes it does help, but then it just opens up the door for, like, you know, just the next level of complication. You know, so where do you end up drawing the line? Basically, there'll be another layer of complication and then another layer which gets added on. And then before you know it, you're just doing templates everywhere. And yeah, so if you don't have templates, what you have is macros, and macros feel dirty. And the best thing about feeling dirty is stuff will feel too dirty and you don't want to use them anymore. So we literally just define custom types like this for our global array. This is I call it a stack because instead of a vector because a stack push and pop. That's just what I come up with. Not so many people use that name, but yeah, we generate these guys, da-da, and that's it. And these are all void types, and thankfully you don't have constructors as well. It's another thing as well. Constructors, man. But yeah, so that means this function is like stupid simple. It's like, hey, find the new pointer to where the elements can be inserted. Up the new count, basically do an assert and return the pointer. Job done. Easy peasy. I've only done some basics with micro processors in C, but I work in C Sharp usually. Oh, okay. All right, so you've been, yeah, I know what you mean, like Arduino and stuff like that. Cool. Yeah, C is lots of fun. So the other thing as well, finish up on that thought I just said. I obviously do go a little bit more complicated with this stuff. Like I got a hash table, right? I do want to like revisit this hash table, but I think I'll keep it in the same sort of level of madness, right? When you need some type safety, you have the void function still, right, which just takes in the sizes, but you like, have the type safe wrappers, which are again in this sort of very dirty feeling thing. But when you start going further with this, it feels dirty and stops you doing crazy stuff. Whereas if you make stuff like templates, you'll just find every excuse to use it if you're not careful. How much yeah, on pick processors long time ago. Cool. How much time is used to just make the engine? How much time actually making the game? So yeah, we was having this thought before in the past. So I spent 60 or 70 streams, was it? I don't know. Or 69 streams. Working on the engine side. And I think about around episode 60, I was like thinking that we're just making an engine at the moment, and it would be nice to be, I'm making this new engine feature, and it's like, will I actually need this for the game that I'll make though, right? And then you're just sort of chasing cool instead of like chasing what you need. So I decided to, pray to God and ask for an idea. And I believe God gave me this idea, and it's on YouTube channel. There's a, if you're interested, you can go and watch the video. But basically, yeah, I won't spoil it. You can watch the video. It's good. So now we're actually trying to make the game, right? The game is going to be called, or the code name, or maybe it's the full name. I don't know. It depends, right? How good is it? Good, you know. But the code name is "Man shall not live by bread alone," right? The Matthew 4:4, and so I would now have a vision. I have a game design. I have the notes in the repo. I have a direction. So now we're building the stuff we need to get prototyping and build the prototype. The engine stuff is basically there, although we've had to come in here and do like a voxel map and stuff like this. But yeah, we're just getting up a voxel map. Well, yeah, just, right? But anyway, we're making a voxel map, making entities, right? Voxel models. We've already kind of got most of the way there. And getting a basic movement going and getting a start to end, and then start fleshing that out a little bit more each iterate, and work on the prototype basically. So so do you decide to do engine because you lacked ideas? No, no, I've found it fun and interesting to understand how things work. and um, also it's nice to know, like, also as well, when you like look in the old days of how games were made, people made engines, right? So it's kind of like being inspired by just by history, and also wanted to know how things work. And also when you use custom engines and stuff, they have their own restrictions and things like that. You know, they have they've made decisions, and you have to live with their decisions, basically. You can make changes to some of these engines, but then that becomes its own slew of problems. But yeah, I go over the reasons in that video actually on YouTube why custom engine. But I've been, you know, building many little game prototypes for years now. Just not really deemed them worthy enough, basically. But yeah, and also building many little engines as well for years. So it's not really a new thing. Um, yeah. But yeah, some of you guys might be happy to hear, or not so happy to hear. I did my first proper vibe coding. It wasn't on the engine. It was on the, well, it's in the documentation now. But yeah, you know, vibe coded this thing because I asked this generate me some image for this stuff, and it said can't make images, but it can make HTML pages. So I was like, oh, okay, make me some HTML pages. So we've got this stuff now. So this helps us reason about what's going on, and you guys can sort of hopefully understand things better rather than just me trying to send you guys words and you got a picture in your brain. So this is what we're working on next, is the actual voxel allocation in the material data, basically, and how that works. But I need to take a quick break, and then we'll get back and look at this and start working on it. So this is what's going to save us a whole bunch of memory. It's going to be cool. And things are going to be packed into cache lines. Look, cache line. And there's hot and cold cache. Pretty cool. Yeah, this is a 2D representation of the 3D 3D world, yeah. That's right. That is correct. Right, BRB. All right, welcome back. So the next problem we need to solve is storing voxels and stuff, and allocating the pointers to, or the indices rather, to the start of the array for the voxel material indices. So effectively, we saw that we have an array of these node hots as we're traversing through the hierarchy. So this is the red here is a block. So it's the 16 by 16 by 16 voxels, right? This is a 2D slice of a 3D representation. Now, what we have is, this is a final 4x4x4, and this is another final 4x4x4. And if we, so when we shoot array 3, basically, and we're stepping through these bit sets to know which children are active and stuff like that, we can, clearly see, and you say you go to this one here, you see they sit in the same cache line, right? And these are the hot ones. So we're more likely going to be accessing this data rather than the cold data. So the cold data is in a separate array because it only will ever get looked at when a voxel gets hit, right? Or when the child gets hit, right? The child node, which ends up in this final case being a voxel. Now, because inside the block, the children are these other nodes, right? The leaf nodes. Yeah. So the issue we're trying to solve now is when we're trying to set a voxel and add it to a block, it changes how the material indices array is allocated. So there's two cases when this can happen. When you clearly add more voxels, it will literally add more, it will require more cache lines, right? But if we use less bits per voxel, bam, right? It needs less data, right? So if we hover over here, we see we're doing 4 bits per voxel. So in this case, the top 4 are stored. This is a U32 word. If it's 4 bits per voxel, 32 divided by 4 would be 8. So you have 8 voxels that it can represent in that area. And so as you see, if I hover down here, they get highlighted differently, right? So there and then there, yeah. So, but you can also, if you're only going to have 2 different materials inside of a whole block, that's 1 bit, and it does 2 whole nodes, right? Which is pretty cool. And if you don't have any thing in here, it just does the next 2, right? So it's all pretty condensed and packed, which is great. And so this can really help us save memory and do big worlds and stuff. So the materials will get changed. How does changing the bits per voxel work? What are you changing? Why do you need that variation? Right, so how the number of bits per voxel ends up changing is because when you set a new voxel, or when you take away a voxel, it's going to either add more colors or make less colors inside of a block. And this will allow you to make a different material palette, and that material palette will, what can we say? That material palette will have a certain set of colors. And if the material palette is only 8 different colors, then that means it fits into 3 bits. So it's 3 bits per voxel. And you can then end up using less space to represent all your voxel data. And if you end up having, say, 128, or let's say 255, up to 255 different materials per block, you need a full 8 bits, so 1 byte per voxel, and you need more memory. The reason why we do this is because we want to save memory and because we're trying to render massive worlds, right? Or a massive level. That's the point. And I want it to all just stick into RAM rather than put out to disk and all this lot, and make it faster to traverse. Do you use different palettes for each chunk? Yes. But we're going to try and deduplicate the palettes as well. That's another thing. So we'll probably go over all the blocks and figure out like yeah, that's something we've got to try and solve. So how do we get this thing going? Weird. But wouldn't using a fixed one for the entire world compress it more? No. Maybe. So if you do one for the whole world, you are limited to 256 colors, which is a no-go. If you do 1 byte per voxel. But if you do the whole world with, you know, you would probably want, after 1 byte per voxel, you want it to be in ranges of bytes rather than bits, I think. Because then you start, well, yeah, you do. Oh, well, up to 10, right? You can have 10 bits. Because 10 bits is the last number where it fits evenly into a U32. So that will be, you'll waste 2 bits at the end, but yeah, it will be, 3 that fit in there. So 10 bits gets you 1024 different colors throughout the whole world, but still a bit limiting. So you do one palette, 10 bits each per voxel. You're still, yeah, and you're wasting those 2 bits as well. That will get you. That's probably the least you could do it if you're going to do that solution. 256 colors is too restricting. Or if you wanted to just not have to care about it, you would do, 16 bits per voxel, so 2 bytes. Now that, somewhere between 10 bits and 16 bits, that will then mean so it would be more simple because then you won't have to, well, you won't have to deduplicate a whole bunch of different material palettes. You would just deduplicate the materials inside one global palette. And then each material palette, I'm hoping you'll be able to deduplicate the palettes across quite a lot of areas, basically. That's the plan. quite a lot of different blocks. You should be able to deduplicate it. And then it should be so each block holds like a U32, so it's 4 bytes. You would be saving that if you did a global. And then yeah, I think it just entirely depends right on how your data is, right? If you on average end up at 8 bits per voxel, you might not be saving. Yeah, if you end up on like 8 bits per voxel across every block, you might not be saving. But if you end up on some of these lower ones, you probably will. I'm not sure though. I have to see. Comes to mind in my system for ASCII decoding. Maybe something similar can be used. Not sure what you mean. Seem to want to use a lot of different block types. Yeah. So what we're doing is each block is going to be procedurally generated for the terrain, right? So it's going to be a unique shape, but the palette can probably be reused. That's the idea. But there might be some with slightly different colors and all that. But yeah. So right, where do we go next? So we're trying to insert a new right, where do we go next? So we're trying to insert a new voxel into the leaf node. So yeah, it does get a bit fiddly. So I've got this thing called a material index. Yes, I think we do nothing here. Yeah, I think this code is all left alone now, basically. So we say if it's a leaf return. Yeah, so now we're into this sort of code here, where it's actually trying to set the voxel. So this is where it does get a little bit fiddly, and we just got to try and work this out. So we've got a voxel material index, and I don't know what that is. So it's just E32. So yeah, the issue is this voxel map is in its own module separate the graphics system, and it doesn't really have it doesn't really know about material palettes, right? So I think when you take it knows about material palettes from the sense of in the block it will have a palette index, but how it gets it yet we don't know. Right, the block hasn't been. This is what this code is supposed to be doing. So So every time you set a voxel, you could just traverse everything, collect all of the material indices which are being used, and then sort of work out when we add this new one, does it change the number of bits that we need to use basically, right? That does get quite expensive, and just changing one voxel is a bit much, but it's a bit of work when you change one voxel, but I think we'll have another function which specializes in just changing a whole bunch of voxels. We'll see. But let's just start with a simple case. So one way of doing it is you just you get a unique list of indices, and that will be by going down the nodes and then looking in this indices array and finding the indices into the palette though. Right, it's in the palette. So you do need to know that what the palette is. So I guess we need the idea of a palette inside the voxel system as well. So when you put in a new material, so you don't really need to look into these guys then. You just need to look at the palette and you say, does this palette have this material in it? If the answer is no, then you need to probably deduplicate that palette and then reassign all of the indices by remapping it basically, and then possibly reallocating the chart. Yeah, that should be the way to do it. That's not too hard to do actually. It's just a question of like, how do you do these material palettes? Because there's another interesting optimization you could do, or to get the maximum reuse, and that is you sort all the material indices in order from low to high, and with that way, you could actually reuse a material palette with more materials, but you're only using the first subsection of it, right? So for an example, you might have one where it's like, the first one is brown, the next one is blue, and the next one is green, and the next one is red, right? This is 4 different values, which means that's 2 bits per voxel. And this is this material palette. But in one block, it might only use that brown and blue colors. And so when we want to look into this, try and find a palette to use which has blue and brown, it should be able to reuse this one that has green and red in it, right? So we should be able to have stuff like that basically, where it just is able to reuse those. It's just when we go and you've got to have reference counting and all this sort of stuff, and when you like another problem could be you've removed some of these references, and now what you have is the one which is only pointing to blue and brown is the only one that's referencing this thing, and it could actually deallocate this and then move it to another palette, right? And stick all the references on that one instead, right? So there's, that seems like a problem where it's like you've got to constantly go and see if you can find a better thing over time, right? To sort of reduce the amount of allocations basically of these palettes. But yeah, the other approach would be doing a global one. It would be interesting maybe if we just did some did some maths to see sort of where the line is on that one, because maintaining pallets seems like it's a possible problem to solve. It's just it might be a bit much, but it's possible. So let's just do some quick maths. So if we did like, I still think that 10 bits per voxel is not, it really not enough. Let's just find a thing to scribble in rather than a code file. Is there like a plan? Yeah, we ended up like, right, let's take this thing over and just write stuff in. So imagine if we had 2 bytes per voxel. And the other one is obviously a variable amount. So you do, that's 65. The issue is here is you've got to, so basically you have a pool allocator of materials, right? That fit into a single. The other problem is my, you have a pool allocator of materials. And then that means if you have any materials which kind of change over time, maybe you have like a glowing material that sort of changes intensity. We can't really store those material datas or any we could maybe have a parallel arrays. But it'd be far too much data, right? You would need like a. I was wondering if you could have some like emissive intensity or something like this. Say you did like lava or something like that. I don't know. Some emissive intensity that sort of glows over time, or maybe you just have that as it works off time instead inside of a shader. But let's just ignore that problem. But I think you won't have any dynamic materials, but you could, right? Yeah, let's just say we don't have dynamic materials. So those will all live in a pool of up to 16, 64K, right? So that would mean, so you wouldn't really need a concept of a block anymore in that case. And then that would mean, yes, I think the way to understand it would be, how many voxels do you want to store at most? And then work out, just work out a number basically. Okay, so let's do the other one then. So let's say the variable amount. So variable amount per voxel. This would mean that you have at least, you have a material palette, material palettes which you have to manage, which will have a bunch of U32s times by the number of materials. So a palette is size of U32 times by materials count, and you'll have as many of those as you need pallets, right? And these have to scale to the whole world as well. So if you start poking in more if you start poking in more unique data, more unique materials, you end up will have you end up having more unique palettes, which will drive that number up. So that, you know, it depends how many you have, but we could put a number on it, right? Maybe there's 4K of them. Let's just say 4K. We can always change that number. Size of the average palette? I don't know. What's the average palette size going to be? I was thinking, you know, maybe 32. Something like that. So that's some sort of data which is going to be on the side. We can tweak these numbers around. And then say if you say the sort of average voxel is would you be able to get rid of the blocks as well when you'd be able to get rid of the blocks? That would be, that's another thing as well. There's blocks that add to this. So the blocks will still need you might still want the concept of a block though to store where the material indices are. Yeah, because that will allow you to change how many. Yeah, that will allow you to allocate them next to each other in memory, basically. You can calculate that in code at rendering time, right? In code at rendering time, you don't need to store all the colors. No, I can't. I don't have a runnable version of it at the moment, right? Like, it's in work in progress, so I'm not really going to be able to get that, you know, without writing the whole system first or writing it twice with two different versions. It's just too much work, right? So you just got to do like it on the back of a napkin, if you will, right? Because you don't have time to do that. You know, you could throw it into AI and basically like keep telling it more and keep doing the whole, you know, the whole rodeo there basically. But no, we it should be easy enough just to do it here, quick enough as well. So average voxel, let's say 5 bits. Sorry, 4. No, if we're doing 32, yeah, 32, that'd be 5 bits per. So that mean you'll fit 6. Yeah. So 5 bits. Per voxel, let's say that, all right? So, and the other thing is the blocks will end up having an extra U32 basically. So we need like a number of blocks. So to work this out, you would have so let's say we can always maybe we can work out some kind of formula or something and we just can tweak some numbers. But yes, you are limited to 5,000 materials, and if you go over that number, that's completely fine. Oh, for the glow effect, you calculate all that code at run. Yeah. So that was, you could do it in code. Yeah, you're right. Yeah, we did say that you could base it off the time variable and just do it that way. But yeah, do custom shader code. Basically, that's true. You could do that. 2 bytes per voxel. So that'll be, we need, so should we say number of blocks, and on average they're say half allocated. Yeah, let's just say like a number of blocks. So we can do this based on the, yeah. So if we take the world size is 1024 by 1024 by 1020 by 256 blocks. They're not all going to be allocated, but you get the idea. Let's say on average, let's say we say a tenth of them is 1024 times 1024. Is a tenth too much or too little? I don't know. 20%. So we did 20% of that. Don't do that, please. So we did 1024 times 1024 times 256. Let's do a tenth of them like that. So let's say there's 50,000 blocks. Maybe that's too much or too little, I don't know. As I understand, if you want to have a very large amount of block types, right? So that'll be, yeah, let's say 50k blocks on average. Let's say roughly 50,000 blocks with the number of 2, and let's say, do we do 50% of those? Or let's say, nah. So we did 100,000 blocks with 50% active voxels, something like that. Yeah. So 100,000 blocks with 50% of the 50% of the voxels being active inside of a block, or being something like that. That will put us at, so you got 16 times 16 times 16, that's inside a block. That'll be 2048 voxels per block. Right, so we're getting some numbers here. So we need also materials. I think we could work out this one quite easy. This would be, the block data would be, so we'll call this 1. And 2, I guess. So the block data would just be size of U32, wouldn't it? So it would be 100,000. So 100 times, this would be times 4, right? So that'd be 400,000. The block data. So the voxels would be 2048 multiplied by, sorry, yeah, multiplied by the number of blocks, so we just did 100,000, right? So 100,000 times 2048. Is this way too much? Yeah, that's a number of voxels, and we did 2 bytes per voxel. So because it's 2 bytes per voxel, that will put you at this number here. So basically, so kilo mega, so about 400 meg. That 400k is not kind of right, but yeah, it'd be fine. It's roughly right. So yeah, because either we'll see stuff which is massively different or kind of the same, and then in that way you just go for the more simplest approach. So now this one's a little bit more involved. It requires palettes and stuff like this. So we was imagining if you had, so 0, we'll call this one above 0. We'll say size is equal to, say we had 4,000 unique palettes times, right, so that number is size of U32, so it's 4 times number of materials. So we thought we might do 32 on average, right? So then times it by 4,000 odd unique materials. Is 4,000 enough? Sorry, 4,000 unique material palettes. It's right. So say if we did 128 times 64k, maybe we'll try that. So that's 65536. That's 8 megabytes, right? Let's be a bit more mad about it. So we'll say the size here then is equal to, let's just say 8 megabytes, yeah? That's just for the material palettes. 5 bits per voxel on average. So we got the number of voxels up there. It was 2048 multiplied by the 100k blocks. Is that the number we had before? Yeah, we did times by 2 in the past, which got us to the 400,000. Yeah. So now we're doing instead 5 bits per block. Is that that's 32 in it, yeah, because 4b16. So what can we say for that? So how many U32 words is that? So let's divide by 4. And you fit 6, right? Because 5 6 is a 30. So you fit 6. You fit 6 voxels in a word. Where am I going with this number? You fit 6 voxels in a word. Maybe I need to go back again. What did I do? Right, let's do that one again. So 2048, that's how many voxels per block on average. It's 50%. So the 100,000. So this is how many voxels you can probably have allocated somewhere. So they're 5 bits per voxel. Or we could do times by 8 divide by 5. Is that what we're looking? Yeah, but you want to do some kind of like, it's something to do with the fact that they're in those block of U32s, and they get cut off. So you need to go down to come back up again. And you're looking about how many. Yeah, so we fit that into so how many. So you just divide it by the 5 point. Let's just divide it by 6 then. It's just a rough thing, isn't it? Yeah, it's just divided by 6. No, maybe it's not right. So that's how many, you can treat that as, so it's how many voxels you need in the whole world. That will be do Voxel keep track of on both its palette and materials? So we sort of went over it. The Voxel keeps track of, let's have a look. Voxel shared code. So it's the block, right? So the voxel, the parent of the voxel is a 4x4x4. So we see the parent of a voxel. So these are voxels here, right? These final blue cubes. The parent of that is a 4x4x4, and that keeps track. That is one U32, which keeps track of a pointer to the block index. And this is the block here, which holds a 4x4x4 of those 1, 2, 3, 4 of those nodes. And it keeps track of each block there. Keeps track of the palette index, which the palette has its materials. So the voxels don't keep track of it itself, but indirectly it does know about it. Right, so if you've got a number of voxels and you're trying to say, so if we're trying to say it takes 2 bits per voxel, we would just divide it by 2, and that'll give us the number of, sorry, not 2 bits. If we say it was going to take 8 bits, what am I trying to say now? So if we did 1 byte per voxel, that would be the number, wouldn't it, basically? But so we did half of that, 4 bits per voxel, it would be, so 4 bits per voxel would be half that number. We would divide by 2, right? So I think we're looking at doing you do divide by 8 times by 6, basically, right? 8 bits times by 6, that's the number. So that puts you about 153k, let's say. So yep. And then wait, I'm confused now. So that's the 1. No, that's the 2. I did it the wrong way around. So this would be the 1. So the blocks would be 100,000 blocks times 8, so that'd be 800k. Yeah, so it seems like you're doing 8 meg plus 800. Yes, so it seems like the variable amount is actually going to be more in this case. If we were to have 65,000 different palettes, which might be what goes on. Yeah, mate. But if you get a lot of reuse, then that number goes down, right? So you can't afford to get the material from the pallets corresponding to. Hang on a minute. Hang on a minute. So can't you get the material from the pallets corresponding to color in the lookup? It seems like many voxels are storing the same data. No. The voxels don't store data. The parent node stores where it is. So if we go to this one, is that right? Yes, you see this here, right? You got a bunch of voxels in here, yeah? 4x4x4, so 64 voxels, right? This is the node that is in, right? And that index there, that U31, right, 31 bits of index, that points to the block. And that block is shared, this whole node is shared between the whole, those 64, up to 64 voxels. But each one of these inside the block, they all point to the same place and they have the same. Yeah. So these do have duplicate data. That's right. They would all be these might all be the same for the leaf nodes. So maybe there's a thing you can do here actually. But the bit set would be different. Right, the bit set would be different, but the node, these will all be in the same block. Yeah. But maybe we can change it if we do the global one. But yeah, you're right, this is basically all the same data here, but it's not at the voxel level, it's at the node up, the parent up. But yeah, they all fit in the same cache line though, as well. So it'd just be all the same data. It's an interesting observation there. Yeah, maybe there's something you could do, but it would be different from the other nodes systems, or the other node levels. But yeah, so analyzing this sort of quick bit of maths here, what we see is if you have a high number of, like, 5 bits per voxel, that's so one is going to be the blocks. We can't change that. The only ones we can change is the size of the voxels, or how much the voxels take up in memory, and this one has extra baggage of how much do the material palettes take up in space. So having 32 different colors per block, which is 64 by 64 by 64, with, 64,000 different palettes, that's going to put you up at a lot of memory. And you've got to manage these things. It's effort, it's more code complication. That is a problem. But if you were to reduce that, right? So if you half that number is halved, then that puts you at 4. But this one still wins, right? So if you quarter size that, you get it to 2 million, and then you're still like, but then you're quite restricted on the number of pallets, right? You know, you hope that it's deduplicating a lot, but you know, we don't have a variable. We have on the GPU, we just allocate the upper bound typically. You know, we can reallocate the buffers. I do have that code, but typically I just max allocate it. You know, so this would end up being worse if the map was to get like that. Plus, it makes the internals a lot worse. You know, saving the voxel data doesn't seem to be the issue. I guess the thing is, right, is this number right? Right? Is there actually more voxels? Right? So if I did 20%, right? Is 20% the right way to do it? Let's consider some more napkin maths. So, you know, I said 1024 by 1024 by 256. That's like all the blocks that we could possibly have, that we'll never have all of them. I did like 20% of that. But like, say if we need, if you think about it in slices, right? 2D slices. So do you fill up the whole landscape, right? And you'll probably get rid of all the empty underground stuff. Like, how many like full-on slices will you have? Think about it in that sense. That's another way of doing it. But you know, let's say there's 32 full-on slices that exist, and the rest is just air, or maybe 64, right? And the rest is just air. So that wouldn't be 20% though, would it? So we divide by 256, then times by, let's do 32, see what happens. That's 33 million instead of 100,000, right? It's an interesting way of looking at it. So if we were to adjust some of this stuff, that would really push up the voxel data, and then it would save, right? Yeah, you got to imagine it's a whole map though, and it's 3-dimensional. But if the data, you know, you can have like biomes or whatever, right? And just like grass and stuff like that. There's only be so many browns you're gonna have. There's only be so many different greens you're gonna have, right? So realistically, there should be reuse, right? What can I say? In the game, it's gonna be like, hey, this block is grass. Let's melt on this thing. In the game, it's gonna be like 2D representation, right? Excuse me. This one's gonna say it's grass. This one's gonna say it's dirt or whatever, right? So there'll be some kind of like at the borders a way to like sprinkle some grass in there and some dirt in here to sort of soften it, right? The transition, so you don't just see clear cuts. So the palettes, so this palette will be infected by grass colors and stuff like this. And that what happens on like in 3D. So you get as many unique palettes as there are probably unique crosses between different neighboring tiles, basically. 64 different material palettes. Oh, 60. Okay, the 264s. Maybe I was thinking a different. Yeah, 64k materials for per voxel. Sorry. in the global array. And this one was 64k different palettes. If we were to do the variable voxel approach, basically. But yes, if we were to say increase, so I guess we just need a simple multiplier, right? Divide by 100,000. That's about, let's say 350 or whatever. So we can simply just take these numbers and see what's up. So if we take the voxel numbers were 2s. So the blocks stay unchanged here, so it's just this one. So if we took this and scaled it by 350, so say that'll be 53. Oh, 53,000 thousands. That'll be 53 million. Am I right by that? Right, let me sort this out a sec. So it's times by 100 first to get it into, sorry, 1,000 foot. Damn it. Yep. Times it by, what was it, the multiplier again? Oh, I lost my multiplier. It was 350, wasn't it? Yeah, it was 350. I gotta remember that number. Let's write that down. Right, okay. Right, so there was 153 times 100, sorry, 1,000, to get into the thousands again. Times by the 350 of those, please. Yeah, it's 53 million. So I guess you just put 53M. Right, so that'd be in voxel data. So then if you did that for, right, so that'd be like a trillion or whatever. Sorry, a giga. So 53 times. So it'd be 40, wait. 4 million times 350 is obviously about 1.4 G, right? Gigavoxels. Bum, 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 bum. Yeah, so that's when you start saving, right? If you have, so there is, so when you sort of, it really just depends on how many different palettes you have, to how many different, to how many actual voxels you have allocated. Right. That'd be 53 meg instead of, yeah, so if I took that number, kilo mega giga, right? If we divide it, that's 2 bytes, right, per voxel. Divided by 2. I'm just proving to make sure the maths is right. That gets you back to how many voxels, basically. Then we did a divide by 8 times by 6. We're off by 10. It times by 10. Where did the maths go wrong? But yeah, so it's something like, one of these is wrong. But yeah, we can double check that again. I'm thinking you only need one type value for each voxel, and any material versions can be calculated when the level is read and displayed. Even stuff like how the block merge, you need to calculate this anyway if you're deciding to on submaterials, right? Interesting. Let's have a think about it. Let me digest that. Right, let me just quickly double check this. So it was, and then I'll rethink your thing. So 4 mil times 350. Okay, so it is that number. So if we were to divide by 2 to get it back into 1 byte per voxel, that's 1 byte per voxel. We divide by 8 bits per voxel, that's 1 bit per voxel, times by 6 bits per voxel. Yeah, so I think it was off by 10 there, so 25. I think that is right. So yeah, we did get the calculator up again. What you saying? So 153k times 350. Why is it off by 10? That's very, very weird. We must have... So we did 248 times 100,000 voxels. Right, I might have done 10,000 on one of them. Right, so divide by 8 times by 6. 53. I'm confused now. What's going on there? Right, let's punch that in again. 100,000 blocks. That's how many voxels, right? So if we did... Did I change that block number at all? No, I didn't. Okay. So that's how many voxels. Then we did 2... Right, kilomega. Right, so maybe this number's completely wrong as well. That's already 400 million. Right. So then that'll be, again, 2048 times 100,000 blocks. I think I might have done like 100 or something. And right, so that'll be how many voxels? So you divide by 8 bits. So now you're 1 bit per voxel times by 6 bits per voxel on average. That gets you at, oh, I didn't do 5. Right, I wanted to do 5 bits on average, right? So divide by 6 times by 5. Right, so it's 128 million. Yep, that makes sense. So when you times this by 350 to get up to that sort of other number, which was had, once if you had far many more voxels, that'll get you at 44 gig. And then if you had 1.4, yeah, hopefully we don't have that, don't go that high, but yeah, then you had the 400 mil 400 million is kilo miller, so that would be 350. Yeah, 140. Right, okay. Right, anyways. So that's the difference. Right, I'll try and process what you're saying now. Wait, so this will mean... Yeah, so even if we had the smaller amount... Yeah, those number of pallets... Yeah, so the voxel data really matters to be as tight as compact. And we should have at least... We could probably max allocate 64k pallets. And hopefully these pallets don't go more than 32 on average, basically. And that's what we'll allocate for. And that will put it down to maybe 128 meg of voxel data, basically, instead of 400 meg of voxel data. And that's a drop in the bucket in comparison to the material data, basically. So yeah, it is worth doing this material, doing the more complicated thing, but it's just how do you manage that? You've probably got to say, right, we're reaching nearly the top bound of material data. Like, see if you can find a more, find those ones which are pointing to a subsection of material palette and see if they can point to another one and completely deallocate that one, basically. But yeah, hopefully you can avoid writing that code. Right, so now you're talking about the different problem, right? Let's read what you're saying. So, right, but that is because you have many materials in the game. Right, so you're saying because you have 64k different materials. Yeah, but even if you had 10 bits. Okay. Right. Yeah, that is a reasonable point. Right, let's look at 2 plus. So say we did 10 bit. Say we did at most. So for 1k materials for the whole level. You think so? It might be, right? So that would be, it would be 10 bits per voxel, right? So we can do the maths. Quick maths. That'll be 100,000 blocks. Beep, 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 beep. 100,000 blocks. That's the right number, isn't it? That's 100,000. Good, good, good. Yeah, that's the right number. So divide by 8 bits per voxel. So you got 1 bit per voxel, and you times it by 10 bits per voxel. That's the number. That looks like a good number. So that would then put you at 256 M. Or, and then it's that times 350. I need to remember that 350 numbers is 89 Gs. Right, let's keep that 350 number floating about. Yeah, so we did the global, that would be, let's keep that saved, I guess. If we did the global, that would still be more. If you only had 1,000 materials. But yeah, if you drop that down a bit more to 8. Yeah. So it's close. it does also mean you do save. You save on complication of the code, basically. You don't have to have the whole management code, and which might be more appealing. And you're saying there's that other thing, right? Let's explore that other idea you had, which is a good suggestion, maybe. Your suggestion was your leaf nodes for the voxels are basically all the same thing, right? These cold guys. So they store. Oh, is that what you're saying? Or maybe it's. Lost my memory's a bit vague right now because I'm tired. But it says I'm thinking you only need one type for each voxel, and any material versions can be calculated when. Oh, that's a different thing. When the level is one type for each voxel. Any material versions that can be calculated when the level is read and displayed. Even stuff I had to the block merge. You need to calculate this anyway if deciding on submaterials. You need one type value for each voxel. Right, so you're saying like an enum or something, right? And any material versions can be calculated when the level is read or display. You need to calculate this anyway. I'm not really quite fully understanding that. Yeah, each block is going to be like an enum in the game code, and then we want to turn it into like a renderable form. So that's just going to have 16 by 16 voxels, and it's going to sort of blend in the neighboring block types, if you will. Yeah, not quite sure what you're saying there exactly. But yeah, see, I wonder if we should drop into a different tree, and then you can basically get rid of that. You can do that anyway, no matter which thing you've got. No. They would all. Yeah, you could, right? So you could call the block a leaf, but that'll drop into like a block node instead, and that'll just divide. And they only have these things. They only have bit sets. They don't have these guys. And that will just reduce a bunch of data actually. But that just helps with the tree traversal. And that works on both. Yeah, it's interesting. What could we do? Yeah, 1000 materials is quite a limit. But it might be okay. You gotta have a restriction somewhere, right? If we limit to 1000 materials for the game, that might be fine. I'm hoping more though it is 20% of the blocks are actually used. I think I did. Yeah, it was 20% of the blocks we did, and then something like that. Hey there, Valibus. How's it going? Is there any reason why you're having to store data in the Voxel structure tool or not store data reference? And, oh, sorry, why not store a data reference and have a system that manages the data per voxel and allocate it in a different data structure array? Right, let's have a gander about what, trying to figure out what this means. So, why not store the a data reference and have a system that manages the data per voxel and allocate it in a different... Yeah, I'm already kind of doing that. We've got 3 different arrays. I think this is what you're talking about. So we've got 3 different arrays, right? We've got some node arrays for the hot data, some node arrays for the cold node data. So they're parallel arrays. The blocks is just a thing where it stores some metadata around a larger region of voxels. And there's a heap array for the material block indices. So this is the reference into that data. We're not storing it in the tree itself. It's just the tree at the end points to this data. But yeah, I think we could make the tree end a bit earlier and go into another tree, and that will allow us to save some memory. That will really help with storing all this data. Yeah, I think maybe the global array could just be better. It is going to be like, or meh. For the map only, the global array probably makes sense. Yeah, so say if we had 256 different block types, right? And let's say on average, or let's say we had like, yes, let's say like 256 different block types and they have 4 colors per. I was only going to have 4 colors per block, but they bleed into the neighbor blocks, right? So you'd have so that is obviously 1,000 different materials that you'll be using just for the map, right? But I'm sure different block types will be reusing some more of, the same colors. So we could probably get away with having more block types because of that. So you might be able to get away with having 512 if it's 2 on average, or if it's, you know, around 1 on average, that's 1,000 different block types, and that would be probably plentiful. So I'm thinking maybe 1,000 materials just for the map is fine, and then the characters and stuff can still have like material palettes, and that allows us to do other things. Basically, not tying the 2 systems together so they can have their own strengths and weaknesses. Yeah, I think that might be the approach to do, because then we don't have to write the stupid complicated palette management, which would be annoying code and it's more work. But this is going to take up more memory, which is sad. But it's just double, right? It's just double more memory, right? Just rather than 10 times more, right? So it's probably a worthy trade-off and probably manageable. Um, Instead of having separate materials for grass with small amount of mu, I'm not sure what mu means, but maybe I'll understand in a sec. Maybe you can use a mostly empty, oh, mud, right, amount of mud, I see, right. Maybe you can use a mostly empty mud stencil on top of any grass that need it. Could that help? So having separate materials for grass with a small amount of mud. I see, right. Could you, right. Maybe you could use a mostly empty mud stencil on top of any grass that may need it. That could help. Right. Yeah, so I'm not doing like separate draw calls and stuff. It'll just be one draw call and we're ray tracing through it. So I won't really have like, I'm not sure if you're thinking about stencil buffers, but use the word stencil. But see what you're saying, maybe like just shading something else on top of it or something. But yeah, I guess I'm trying to avoid very custom shadery code like that and just having it in the material data and stuff. But yeah, hopefully that answers your question. But yeah, I think, right, so I think this approach will be better. We can go down that. It will require a slight change, but it means though, right, we could probably get rid of, right, so let's write a little to-do down. This is cool. And yeah, cheers for all the advice, by the way. I do appreciate it. I appreciate your questions and things. It does allow us to think about these things a bit better. So the to-do list is you know, right, so use, you know, global material palette for the global 1K material palette for the map only, right? Right, so the voxels, the voxel models still allowed material palettes, right? Then you've got a one or, sorry, the two was, you know, we want to have a separate, so the leaf node is now a block, right? Leaf node is now a block. So that's the 16 to the power of 3 voxels. And this will put you into a, I guess, 3. The block is now a tree. Now its own tree. Of 2 by 2. No, a block would just be its own. It'll basically reuse the node hot. Its own array of voxel map node hot. Maybe. And then the block. I mean, instead of having a pixel pick by like 30 different material versions for grass, you could just pick the grass and an additional mud stain. That way the amount of material version becomes a lot less. Right. Just, right. Yeah, I'm not sure if there's gonna be a muddy grass block, right? Of sorry, Voxel, I meant to say that lingo. Yeah, I'm not sure what would. I think we're just gonna um yeah, that blending between the two. I think the way I'm thinking about doing it. So say if this is like grass, right? This is mud or whatever, right? No, it's my reason for having many materials. I don't think it was my reason. I think my reason for having many materials was, yeah, I don't think it was my reason for having many materials. That might be a misunderstanding there. But the idea was the materials from this block, would like, say there's like 4 different grass colors. Some of them would just go over here or something like that in the dirt, which has again its own 4 different colors, and some of those dirts will go over here, just little voxels to just offer some kind of blend, maybe like a did like a um the classic patterns like a dither pattern, these guys between the two boundaries basically. That's what I was thinking of. That's where the confusion might have came from. But yeah. So we could say the block is now just its own of hot array as it doesn't need cold, right? As the cold would all be the same values anyway. And then we need to, so that means then the block would need do. So that way, so you have this block, so it means this voxel array can be variably allocated basically. And inside some kind of region. Maybe 16 by 16 is, maybe we could change that. But yeah, effectively you need, you still need a sort of a voxel map block to store. So strut vox map, and then you need like a U32 to store the sort of root. No, what do you need to store in there? Sort of the voxel material indices and probably the root node. Is its own little tree. So one level. No, because no, it's the final leaf node. That's a 4x4x4. And are they all the same actually? No, they might not be the same. And trees are so confusing. There's trees. So yeah, they would always point back to the same block, so they were all the same. Right. That's the final 4x4x4. And that's right. So there's a one above. Yeah, so we could say it's not really, It's not really a block then. You can probably call it a sub-block. The sub-block we'll call it. We'll think of a better name now. So you probably have voxel, brick and block, maybe. Maybe you can call it brick. This is another common name for these things. Yeah, but that will do it. You still need a strut. But yeah, that means you'd also need an array of bricks then, basically. It just kind of sucks. Maybe we'll do this. We'll think about it. But the brick will do a root node, and then it'll point to the block index, maybe. Yeah, we've really got to think about this a bit. I don't know. Yeah, it's a dag. It's a dag. So it just goes, it doesn't loop around, basically. Right, you want to ingrain these into each material and make them variants. Go up to... the only reason why I went up to 64k materials is... You want to ingrain these things into each material. Yeah, I'm a little bit confused now, to be honest. I think we worked it out in terms of the materials that we need is only 1,000 for the whole map, basically. 1,000 different materials is probably plenty. The reason why I wanted to go up to 64k though, possibly, is because as for the number of pallets, I think, because they were maybe going to be unique per block. But we found out that was probably not. It could end up saving, but maybe not. So we'd probably avoid that. But yeah, there's stuff to think about in terms of like that final level. There's maybe some savings there, right? 3, maybe savings. The final level of 4x3. Or the second final. Wait, which one is a leaf? So that'll be... It will say it is a leaf. That'll say it is a leaf. But also it is a leaf and point to the same thing. Yeah, so it's the final level of that. Cold will all point to the same block. So probably some savings here. And we'll pop that there like that. And we'll think about that. Right, so stuff to think about. But yeah, we could probably go to this sort of approach and stuff to think about here. But I got to put a pin in it here today. But I'll have a think about this off stream some more. But yeah, good progress nevertheless, because we've now been able to save some complication at least. It's just, yeah. Yeah, just got to think about this one some now. But yeah, the next stream will be Tuesday at 7:30 p.m. GMT +1. Usually there's a stream on Thursday, but I might have to cancel that one. But you can check out the schedule down below. 7:30 p.m. PM GMT +1. Tuesday, Thursday, and Sundays. And there's another stream on the Fridays as well at 2 p.m. GMT +1. But yeah, in the meantime, guys, there's a Discord channel. If you want to come hang out and chat off stream and talk about anything programming related or the Bible or stuff like that, you can come and hang around. And there's also a YouTube channel if you want to watch the video, seeing what the game's going to be about. Go and check that out there. And also, if you want to support the stream and get access to the code for the whole engine and the game as well, the code is all on a GitLab where you can download and run it on your own local machine. We're currently let's just say halfway through the voxel map data structure, and then we'll be able to check it in probably when it's rendering. So that will go up whenever that's ready. But yeah, thank you for everyone who supported the channel. Appreciate you all. But yeah, I'll hopefully see you all on Tuesday, and maybe, yeah, I'll see you in a future one. Right, God bless you all. Hope you have a wonderful start to your work week, and I'll see you all very soon. Right. Bye-bye.